Welcome everybody to our second OptiSystem webinar session. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave. I'll be working alongside your host, Ahmed Attia. Today we'll be discussing basic link design and analysis using OptiSystem. And before we begin, let's do a quick overview of the webinar structure. So during the presentation, I'm going to launch 3 polls. If you're present for all 3 polls, your name will be entered into our $50 Amazon.com gift card draw. The winner of these draws are announced on our website, and the draw for this will be announced at 2 p.m. Eastern Standard Time, so basically 1 hour from now. We're also going to have 2 question and answer periods at the halfway point of the session and at the end of the session. As in previous webinars, we're not going to be answering any questions via the raised hand option that's in the GoToWebinar control panel, so please type all your questions into the questions section only. We also have 1 handout available that you can download at any time. Finally, we're going to be recording the webinar and distributing it to all registrants via a download link. You'll receive this link tomorrow at 2 p.m. Eastern Standard Time. So 24 hours after we close out the session, you'll get an email with the recording. Well, now it's time to start the presentation, so I'll pass the mic to our Director of Optical Systems, Ahmed Attia.
Okay, hello everyone. Today's webinar would be about basics, examples, and analysis for the OptiSystem software. The webinar would be in it, I'm going to talk about, give you some introduction, then I'm going to concentrate on signal representation in OptiSystem software. Then I'm going to describe an optical fiber transmission link, which we will use as an example here. We're going to do a few different presentation of the link and design. And then we're going to talk about how to set up some parameters, which is important in this link, like the fiber parameter. And finally, we're going to run the project and show you different cases. We're going to look at 4 cases. One of these cases would be just regular link, and then we amplify it and compensate it, and then we do some kind of sweeping for gain of the amplifiers and power of the laser, and also look at the issue of randomness in the results of the simulation. Okay, so first thing is, like yesterday's yesterday's webinar, we were talking about how to select component, and we looked into the OptiSystem software, and we looked at the libraries, and we kind of looked at how can we pick up components and drag them into the canvas and set up a project, either electrical components or optical components. And then also we kind of talked about the example library, which is important for anyone who wants to build his projects on it, or use it as a basis for his examples or his project. And also we talked about documentation somehow, and one of these documentation we talked about it is the component library. And in the component library, it's very crucial and very important for this, like, I mean, when you design your project and you want to simulate it, it's very important to go over the component library to understand how to set up the parameter, how to understand sometimes the theory. It's important for making sure that the component works as you wanted in the example. Then this documentation about the component library, again, we can access it through the link which I show here, or you can access it through the help button, which you go, for example, through, if you go, for example, through component property, as you see here. For when you click on the component, double click on it, you're going to see the component property. And if you click on the help button here, you're going to get out the document of this component, and you can scroll through it, see the definitions of the ports, the specification settings, and the theory. Okay, so Now, one important issue also in the simulation, when you run it, you need to use the proper signal representation, which is mainly in this presentation today. In this webinar, we're going to talk about different representation and the differences in the usage of each of them. Okay, so now there is 3 representation of the signals used in OptiSystem. One is sampled signals, the other was parameterized signals, and the third one is noise bands, basically for the noise. Now, for sampled signals, yesterday we mentioned about optical signals. They usually at the output of every component, they are in the frequency domain, and in the for electrical components, they are in the time domain. Now, for the optical sampled signal, basically they represents the complex optical field. So you're going to have the magnitude and phase, and it's defined into 2 polarization, which is defined as X and Y in the simulation, and it's also defined over a specific band of frequencies. Now, in terms of the electrical samples, when you use the electrical samples, if you want to use it as individual samples, you have to use a component which is called convert to individual electric samples. This is, you have to place it in front of the component which you use, for example, signal source or signal generator or whatever. You have to put this component after it to be able to convert the signal into individual samples. The second type of signals which is used in OptiSystem is the parameterized signals. Now, the parameterized signal is a kind of representation as an averaged signal for the whole samples of that signal. If the signal is optical domain, the average would be, if the signal is in the time domain, would be, as electrical signal, would be time average. If the signal is optical signal, would be frequency averaged, and represented as basically a single power and a single, for example, frequency. Now, the last representation of signals, which is the noise bands. Typically, the noise bands are defined as you see here, for example, in this picture. Where is this? Just a minute. So, in this picture here, for example, you can see the noise bands. The noise bands basically defines the average noise power per frequency range. So it's like a power spectral density, and in that scenario, the noise bands are defined. Where we are. Okay, so the noise bands again is defined as power spectral density for the noise generated inside the components. Now, again, the signals for optical signals will be defined in the frequency domain. Electrical signals are defined in time domain, and sometimes some other components like DSP, MATLAB components, you can define the output to be in the time domain or frequency domain. Now, when you have, for example, 2 signals propagating in a component, then these signals, if they overlap the bandwidth, then the samples of these signals will be added together. And if the bandwidth of these signals do not overlap, then the samples basically will not added, and they will kept separated during the calculation in the component. Now, sampled signals also can be represented spatially, so you would be able to represent the signal for multi-mode components and use it as well as like time or frequency domain, as well as the spatial representation. Now, for parameterized signal, when you average the signal in the time domain as an electrical signal or in the frequency domain as optical signal, then you eventually gonna get one power value at one frequency value, and this is would be mainly used in applications like if you want to do power budgeting analysis in WDM systems, or you, for example, you wanted to do analysis for EDFA and steady state analysis, like you want to find gain, you want to find noise figure. all of these things can be done in the parameterized signal format. For the noise bands, now again, the noise is described as a power spectral density, so you have average power within a certain bandwidth. Now, this bandwidth is during propagation in the component. It's the width of this noise bands is automatically adapted during the transmission to basically allow the filtering of the noise with a specific, to allow certain precision. The other thing is for the noises, because when you have a signal and you have a noise in the signal, if you wanted to, for example, to do some kind of signal to noise ratio calculation, you need to know the noise floor of these signals. So the noise floor, typically, if you don't have noise bands, is defined as an interpolation process. And interpolation process, basically, it defines two parameters, as I'm going to show you here. So, for example, the CW signal here, you can see it, and then this is the noise floor. Now, based on the interpolation offset, you define where you wanted to get the noise floor. So you can have very wide offset or very narrow offset, and then you can define from that the noise. You can interpolate the value here and the value, and you get the noise value in the middle, basically, as a linear interpolation, for example. Now, for signal also in generation, when you have any pulse generator, typically the signals generated has no noise in it, and the noise is generated in some components. For example, if you look at a photodetector has different types of noises. Can be shot noise, which is basically characterized by time variance, because a time-dependent feature depends on the carriers available, and then the thermal noise, which is characterized by power spectral density. And then in the photodetector, we have also dark current. So all of these types of noises can be set in the component. So once you double-click on the component, you can set the activate or enable these noises. And for example, dark current, you can set the amount of dark current based on the, for example, the specification of a detector you're going to use in the experiments. The noise information basically is created, again, depends on the component properties and noise sources available in the component. For example, as we saw in the laser, there is a noise generated in the laser. We're going to talk about it later on. In the detector, there is noises, and there is other noises, for example, in the fiber when we transmit, and so on. So every component has its noise sources, and depends on the component, you have different statistical representation of the noise. Now, in this example here, which we're going to talk today about after the break, but what we're going to do in the example, we're going to look at an optical fiber transmission link. And in this link, basically, we're going to look at different permutation of the link. First, we're going to look at a non-amplified, non-compensated optical fiber transmission link. And in this link, what we do, we try to change the power of we sweep the power of the laser and look at the performance of this link. And then next, we do amplify and compensate for dispersion in the link. And we change the gain of the amplifier and look at the performance with changing the gain of the amplifier. So we sweep the gain, and then we do another experiment where we basically keep the link without sweeping. However, we repeat the transmission experiment many times, and we look at the effect of randomness of the noises which generated in the system and how they affected the results. So if you remember, we mentioned yesterday about parameters, like if you wanted to look at bit error rate, you need to use more bits per sample to get finer resolution. So if you notice that in these results there is, for example, large differences between iteration to iteration, then you should be able to increase maybe number of bits per sample, and you're going to see that the differences will get lower with the number of iterations repeated. So this is the transmission link, which we're going to discuss shortly after the second poll in the break. the system is composed of pseudo-random bit sequence generator, the pulse generator, Mach-Zehnder modulator, and the laser, then a fiber, and detector, and a filter. So this is exactly the system which we studied yesterday. And then today we're going to add up to it again, as I mentioned earlier, amplification, compensation, and then we change the gain of the amplifiers, and we look at the different cases here and the feature and the effects on the quality of the transmission. At this time, I'm going to take a break, and we're going to go to the second poll, and I'll go, if there's any question, I'm going to take a look at them, and we continue after the break. Thanks very much for listening.
Okay, I've just launched the second poll, if you guys can take a second and answer that. And also, I'm not sure if everybody here is registered for the other OptiSystem webinars, but we have one tomorrow at 11 a.m. on advanced features, another one on Thursday with the advanced applications, that's at 9 a.m. in the morning Eastern Standard Time, and then a final one on Friday at 9 a.m. in the morning as well. Advanced Applications 2, we titled it. So if you haven't registered for those and you're interested, feel free to go to the website quickly and register for those. If you just go to optiwave.com, and you'll see on the front banner the webinar week, you can just click there and you'll access all the webinar sessions. And again, that's going to be the same page where we're posting the $50 gift card winners. And also, if you want to get the recording before the 24-hour period passes when you get the email with the link, you can always go to the same page, the webinar page, click on any of the webinars that have already passed. Half an hour after the webinar ends, the video should be posted on that same link. You just click the link, hit register again with the same information, and it takes you right to the recorded video of the session. Okay, I'm going to close the poll now and pass it back to Ahmed for any questions.
Okay, thanks, Brian. And I just wanted to mention that the presentations I'm talking about right now, you can download it from the webinars here. It's attached, so you just only double click on it, and you should be able to download it. Now, going back again to the project which we're gonna here calculate and see, for example, before, if you look at again on the project here, what we have here, we have a laser diode, which is mainly, as we mentioned earlier, is a source of noise. We have the detector, which is a source of noise. And if you run the simulation, ideally, many times you should, every time you should have, because of the randomness in the sources in the detector, because of the pseudo-random bit sequence randomness in it, the length of the sequence, all of these things, you're going to have different performance at the output of the transmission link. So one of the things which is important to look at it right now, I'm going to show you how to see the effect of randomness with the laser diode here. So if you look at the laser diode, we have a feature on the laser diode where you can control the randomness numbers. So there is something called generated random seed. So if you look at the at this figure here, if you double click on the laser, and you can go to the component properties, and then the random numbers in here, you can see generate random seed. This is if you click it, it means it's true. And there is another field here which is called random seed index, and this is a number which you can enter 0, 1, 2, whatever number you're going to enter, and based on this number there is a noise generated based on it. So you have two options. One option, if you for example choose the generate random seed, it means this additional, there is an additional noise added to the seed which existed, because any laser will have typically a noise in it, and this seed is random, depends on different models used, either Gaussian models or gamma models. There is different models used to generate the seed. Now, if you don't choose it, which means this is false, there is only one type of noise which is generated for the laser diode, and it depends on the number you enter here. Now, if, as you see here, if you click on this or you choose the generate random noise, basically the field here would be gray, so you cannot enter the number. But if you don't click it, then you can enter a number here. Now, the difference in the performance, if you see here on the laser spectral profile, for example, when you check generate random seed, the output here of the laser, you can see different outputs and different noise background generated. So every time you run the simulation, you're going to get a new different noise in the source, and sometimes arbitrary small differences between the power levels of the laser. However, if you choose the false configuration, as we see here, then again you can enter whatever number here. They generate different types of noise levels, but as you see here, it is the amount of power generated in the laser. If you repeat it as many times as you want, every time is going to give you exactly the same power level and exactly the same noise level. Okay, so if you wanted to do any calculation without any like noise generated into the laser, so basically you can don't choose the generate seed function. This is one thing. The other thing is if you go to the detector, as we mentioned yesterday, you can choose the noise sources you wanted to have, shot noise, thermal noise, or you can have, for example, the dark current. You can also control the responsivity, which is you can get these numbers from either you enter it as data from the vendor, so it will be wavelength dependent or would be constant across all wavelengths. So these parameters, as we showed yesterday, you can have some control over it. So now in the code, if you want to go through the code here, so in the code again, each component here, we can click on it, double click on it, and then see the parameters in it. So in this project here, I created two layouts, as you see. The first layout here, which has these designs duplicated without amplification in the first one. However, the laser is swept between minus 10 dBm to 10 dBm in 10 steps, and the one linear was variation, so the distance between power to power is constant. And then the second configuration here, I added up an amplifier and fiber. I'm going to talk about the parameters of it in a few minutes. And then we can change the gain of the amplifier here through a sweep. So we can see it in the second layout. So you can see like second layout here, the gain of the amplifier is swept from 2 dB up to 20 dB. So every time, every iteration is going to run, you're going to go get different gain, and then you monitor the performance of the link. This setup here, what's the difference with it? We don't sweep the laser or the gain. We kept it only one setting, and which is here the power of the laser is 0 dBm, and the gain here is 20 dB. And basically we repeat this is 10 times, and every time we can look at the performance and see why the effect of the noises generated here, because every time you generate different noises, it affects the simulation results in here. So if you want to improve your accuracy of the measurements and decrease the dependency of the noise, you need, for example, to increase number of bits per sequence, and do the simulation will take longer time, but it should give you closer results between run to another run. Okay. Now, in terms of the components which we need to talk about it now, is the two components is mainly the fiber and the dispersion compensating fiber. So basically, the fiber here, you can control the reference wavelength, which you can define the parameters like attenuation, nonlinear effect. All of these things can be defined on the reference as reference or calculated at the reference wavelength. So if you use defined here, if you click on it, then you can enter the reference wavelength, which here attenuation, because we choose constant, it means all the wavelength will have the same attenuation. Else you can, again, as we mentioned yesterday, you can choose a file and you can vary the attenuation across a wavelength. Now the attenuation is 0.2 dB per kilometer at 1550. So if you have another wavelength, there would be some kind of calculation. If you have constant, it means you have still 0.2 dB. If you have a file here, then you're going to get the attenuation at that wavelength. Now, if you go to dispersion, you have the dispersion value now 16.75 picosecond per kilometer nanometer is set at or evaluated at 1550 nanometers. So if you wanted to go, as you see here, beta 2 is the group velocity dispersion. The value here, -20, it's in gray, so it's not representative to the actual value which is used in the simulation. So the simulation, if you wanted to go to the simulation, basically you can use the relationship which is used inside the code, which is dispersion equal -2 by c over lambda square beta 2. So beta 2 will be calculated from the dispersion value, which is at 1550, and this is the lambda used and the speed of light, and then you get the beta 2. Now, this beta 2, basically, it's this beta 2, just a minute, please, okay. So the beta 2 will be not -20, but will be the exact value, which is evaluated at 16.75. Now, if you go, for example, for nonlinearity, the values here again, if you use effective area constant, then it means all over the wavelength would be the single value, which is 80 micrometer. If you use it from file, then you can have, for example, effective area wavelength dependence, and so every wavelength may have its own effective area. Same thing for the nonlinear refractive index. Nonlinear refractive index here, it's set up as constant, which means, again, all the wavelengths have the same value. If you use it from file, then you can have refractive index wavelength dependence. Okay, now the value of N2 used here is 26×10⁻21 meters square per watt. Again, you can use enter these values from manufacturer. We have, as mentioned yesterday in the library, one of the libraries, which is, there is lots of files describing different types of fibers, parameters, so you can download these files and use them, for example, in the calculation if you have DWDM systems where you have multi-wavelengths and you need to look into each wavelength's performance separately. Okay, and then nonlinearity here, if you look at the nonlinearity, you can choose cell phase modulation in this type of fibers. Yesterday I mentioned to you that there is another component which is called CWDM fiber, where you can control the cross-phase modulation effect in it. Here, it's not calculated in this type of fiber because it's single wavelength, but if you have multi-wavelengths, then you can use the other type of fibers and set up your cross-phase modulation effect. Then you can do the Raman effect, stimulated Raman scattering effect. And if you have, for example, very narrow pulses, you can use self-steepening and other nonlinear effects. Now, the other component, if you see here in the project, is the dispersion compensation fiber. Now, the dispersion compensation fiber is the same type of fiber which we used earlier, but what you do here is you change the parameters of it. So, for example, dispersion compensation fiber, typically the attenuation is around 0.5 dB per kilometer, so you need to change this. The length, you enter your length of the dispersion compensation based on the dispersion value of the product. For example, here we have so you can enter -100 picosecond per kilometer nanometer, and also the dispersion slope for dispersion compensation fiber is different than standard fiber, so you can enter your own value as well. In nonlinear parameters here, you have to make sure also the effective area is different, because for dispersion compensation, so you have to enter the proper value in the calculation, and same thing for the nonlinear refractive index. Once you enter all these parameters, basically you can rename basically the component here and call it, for example, dispersion compensation, which is, in principle, it's the same fiber component which you used earlier. Other than these components, which we talked about them yesterday, the pseudo-random bit sequence generator and the pulse generator is the same. The laser, we talked about it, and the detector as well, we talked about it yesterday. And here we use, for example, responsivity 0.8, which is about typical for detectors for WDM systems. And then the noises here, we create, we add up the types of noises, we add up the dark current and thermal noises as well. And the filter, we talked about it yesterday. This is, you can use different types of filters. And then the bit error rate tester here. One thing which yesterday I didn't mention is how to connect the bit error rate tester. As you see here, we have different components. Some components in the component library, you can find a receiver which has built in the components together, or sometimes you have to have separate components, as you see here, detector and filter. Sometimes you have 3R generators as well built in the same component. So you can explore the different components in the library, which is in here. The bit error rate tester, the first line here, the first connection is coming from the pseudo-random bit sequence. So you need to know what did you send. And then also the pulse generator, another line, and the last line is the output of the system. So the order of these things sometimes it has to be clear, because if you mix them up, you might have a problem. You don't have any output at the bit error rate tester. Now, as I mentioned earlier, any component, if you wanted to look at the property of it or how is the parameters is set, you just press on the help, and you can see all the parameters outset, technical background, all information. Sometimes there's references for the models used. Now, you cannot double click on the visualizers, as you see here. If you want to look at the help of the visualizer, you need to go with the right mouse and go component properties here, and then you get the parameters of the visualizer, and then basically you can read about it, all the details which you need for that component. Okay, so for the time now being, I'm gonna run the project here. As you see, again, we have two layouts. One layout which has this project for sweeping the power of the laser, and then without amplification, without dispersion compensation, and then we have sweep also still power of the laser, as you see here. So we sweep it between -10 dBm and 10 dBm. And then what we add up here, we add amplifiers and dispersion compensation fiber, and then we can look at the performance of this bit error rate tester for displaying the outputs for 10 iterations. And then the second layout would be adding up the sweeping of the gain of the amplifier between 2 and 20, keeping the power of the laser is 0 dBm, and then look at the performance. And here we fix this diode 0 and the gain 20, and we look at the performance and see the effect from one run to one run. So once you calculate the project here, the project is going to go through the layouts, which is the first layout and the second layout as well. So it's going to repeat itself 10 times. So if we run calculate now, it's going to take a few minutes. One thing which if you look at the window here, calculation window, you're going to see timestamp here, which tells you how long this calculation process will take. So if you run here, you can look at the sweeping here. So it's right now doing version 1, which is the first layout, and iteration 1, iteration 2, and so on. So it's going to take a few seconds here, or maybe about a minute. Now, in the presentation which we're going to give tomorrow, my colleague is going to give you about the scripting and how to use the MATLAB component and the C++ component. I'm not sure about the Python component, which is going to be released in the next release version 15. He's not going to give it in tomorrow, but after a few weeks, we're going to release the version 15, OptiSystem version 15, and then after that, we're going to make a webinar to show you how to do the Python component. As you see here, for example, right now it's going to layout 2 and sweep 2, so you can monitor it. It's taking about 1 minute so far and 7 seconds. The other thing is we're going to do in the advanced OptiSystem webinars, we're going to talk about how to automate the use scripting to automate the process of capturing bit error rate versus received power for different advanced modulation schemes. As well, we're going to talk about Raman amplification. So these are the two advanced webinars which we're going to talk about it in the next few days. So now it's the iteration number 9, and it's 10, and it's very close now to stop. So it's wrapping up the components. As you see, the calculation of the components goes serially, so it starts from one component to next component to next component, and so on. Okay, so the project took to execute 1 minute and 51 seconds. Okay, now if you look at the, for example, first layout here, and you click on the bit error rate tester, and this is the bit error rate tester, and you look at the I. Now this is the I at so this is the I for iteration number 10. Now if you look at, now don't forget this is at power level of 10 dBm. Now power high, you expect to have nonlinearities in the system. So you have the I is closing here, bit error rate is around 10⁻⁵. If you go somewhere in power level lower, you see also the I completely closed. So basically the system is not working. If the other thing is, if you see in the system here is the system is not compensated. So you have dispersion in the system, you might have nonlinearity in the system. That's why the system is not working. If you go, for example, for for example, iteration number 8, you have also the I closer, so you need more power basically to enable. So this is the highest power, which is 10. This is the best scenario you can get, which is about 10⁻⁵. Now, if you go to second transmission link where you add up the dispersion compensation and you have a gain of 20 dB, which compensates for the losses here, and basically, and still sweep over the different. So you can take a look at the performance here. So you can see, so if you look at the I and the Q factor, this is iteration number 10 where you have 10 dBm from the laser and the gain is 20 dB. The bit error rate is -128, is almost like error-free transmission. Now, if you go with lower power, let's say this is the minimum power level, which is -10 dBm, you can see that the I is completely closed. So you can, again, look at different scenarios. The problem with this right now is because there is no scripting to go over all these iterations and store the data. It's tedious and hard working, but again, we're going to show you how to do it automatically in the advanced presentation webinars later on. So right now, for example, iteration 6, at certain power levels here from the laser, you can get 10⁻31 bit error rate. So this is the difference now between this link and this link, where you have dispersion compensation, you have gain of the amplifier to compensate for the losses. Now, if you go to the layout 2, where we kept the power here at 0 dBm and we changed the gain basically from 2 dB to 20 dB. So basically you can compensate for attenuation in the fiber partially, okay? And then you look at the bit error rate, you can see the effect of, again, power level into the fiber. So with, this is 20 dB gain, which is iteration number 10, and the bit error rate is like 10⁻⁹. And if you go, for example, at the lowest, which is 2 dB, the I is closed. So you didn't basically compensate for the losses in the fiber, and then you have basically the I closed and you have bit error rate 1. Now, if you look again at this configuration where the gain is fixed at 20 dB, which is compensating the losses basically in the fiber, and then you have 0 dBm launched into the fiber, so you don't expect to have nonlinearity in the fiber. And then you look at the performance. Now, the performance here, basically what we need to look at is the effect of running 10 times the simulation. And if you look at the results here, you can see, for example, first iteration is like 10 minus 20. Second iteration, you're going to look at different number, minus 19. If you look at third iteration, you look at minus 18. So it's almost the same. The results are very close, like within the range. However, you can decrease the dependence here if you increase the number of bits per sample, so you can have better, stable performance. However, there should be some differences, again, as I explained it, because of the noises generated randomly in the source and in the detector, as well as the depends on the codes which is transmitted in here. So depends on the randomness. Okay, so going back again to the presentation. So we talked about how to set up the parameters of the fiber, and talked about the nonlinearities. Also, as I mentioned, the user can enter the measured data, so either supplied by the vendor, or he can measure the characteristics of certain fiber or certain component and can enter it in the simulations. We showed you here basically the components, different components. Again, this is optical fiber where you don't have cross-phase modulation. With CWDM, you can have cross-phase modulation. And then bidirectional fiber, which allows basically to look into relay scattering, or, for example, application for Raman amplification. So you can launch in one direction and in both directions, basically signals. Also, we talked about the dispersion calculation and the relationship between the dispersion and the group velocity dispersion, as well as the reference wavelength. And we talked also about the nonlinearity. And with this, I conclude the webinar, and I'm transferring the podium to my colleague to run the third poll here.
Okay, so we're gonna go ahead and throw up the third poll. And just as Ahmed already mentioned, the continuation of the OptiSystem webinars is tomorrow at 11 a.m. Eastern Standard Time. So feel free to register for that if you haven't already. I also sent the link for the webinar page in the chat window. I'm not sure if you guys all have that open already, but you can click directly there, look at the previous recordings, the $50 gift card winners, and also sign up for more of the sessions. So again, we're doing this. There's an OptiSystem one every day this week, so you'll have one tomorrow, one Thursday, and one Friday. The Thursday and Friday ones are at 9 a.m. So I think with that, I'll go ahead and hand it back to Ahmed to wrap it up.
Okay, thanks, Brian. Okay, so I have a couple of questions here. One about the nonlinear refractive index. As I mentioned in the setting of the fiber, the nonlinear refractive index, which is N2, you can either set it using a single value. If you have constant, let me show you here. If you go to the parameter and in the fiber, you can have nonlinear refractive index. Basically, if you can set first either constant or from file, and then you put up the parameter which you wanted, and you can use some parameters which is in the literature found, or you can find it in the datasheet of the fiber components. Okay, so with this, I conclude the webinars, and I thank you. There's any other question, we're going to address it through direct emails. Thank you very much for attending. Bye-bye.